everyone. It's a great pleasure to introduce today's speaker, Dr. Emily Harrison. She did her undergraduate studies in physics and geology at the University of Wisconsin in Madison. And when she was a senior, she got an opportunity for an REU study scholarship at the University of Delaware at their ASC Interaction Lab, which is a very impressive lab, by the way. And she liked that experience so much that she applied to graduate school there, and then, so that is where she did her PhD on the effects of rain on the ocean surface. And so one thing I noticed about her past was that she made presentations 3 times at the meeting on ASC interactions organized by the American Meteorological Society. And every time she won an award for her presentation. And last year she was elected to she became a member of the ASC Interaction Committee of the AMS. And now Dr. Harrison works for the US Navy at their facility at West Palestine, Maryland. So let us welcome Emily Harrison.
Thank you. I hope you can hear me. All right. As Sultan said, I studied rain for my PhD, and to motivate this work, I have 2 videos shown here. On the right is a high-speed video of rain taken from above, where the scale in this video is 10 centimeters for the light edge to edge. And you can see rain falling on fresh water, and rain generates a lot of secondary droplets and jets as it impacts the water surface. On the left is a second video, this time rain falling on a saltwater surface where the rain has been dyed with fluorescent dye. And this video is shot from below, also shown in slower speed, but this video, the original video, was at about 7.5 hertz. It's playing back at 5. And the rain, as it falls on the salt water, forms a freshwater lens that is only about 5 centimeters deep, as the salt water isn't inhibiting the fresh water from going any deeper. But here you see where what is forming jets is actually has these large craters forming, and there's bubbles and all sorts of other structures forming, and you have turbulent freshwater lens forming, and all sorts of other interesting structures.
You said shot from above, but it looks to me like it's shot from the side.
This video is shot from above, so this is looking down, so you can see the droplets forming. This is shot from below, so it's at a slight angle, maybe about 2 degrees, so that you're not having the wave field inhibit the velocity.
It looked like I was looking at its side on, no?
It's from the side. When I say from below, I mean a slight up angle.
Okay. But we were basically looking at its side on.
Yes, you're looking at its side on when they're both are side on. So this one is from a bird's eye view from the side, so that you can see the actual impacts and the jets being formed. This one is a slight up angle, so that you don't have the wave field hindering what is directly happening beneath the crest.
Thank you.
That's whatever. So an outline, give you a general outline for my talk. I'll give you a background for why we care about the rain. Most people study large-scale structures, and when you're talking about global climate models, or even large-scale regional models, most people, when they care about rain, they talk about the mass flux, and that's the only thing they consider about rain. They don't care about the small-scale physics. Small-scale physics with rain gets shut from the problem. Why do we actually care about this problem? Why shouldn't it be ignored? And then I'll get into how I actually investigated the rain problem. So there were 3 experimental studies: a rain and wind-induced gas exchange study, a rain and wave interaction study, and then a rain-generated turbulence study, and how the 3 of those actually relate. So why study rain? Rain transfers mass, heat, and momentum to the ocean surface. Rain carries both inorganic and organic compounds. It is cool and fresh in its nature, so it cools, changes the salinity of the upper ocean surface, and it's a small object, but it's going fast, and it slams into that ocean surface. So when it does, rain has been observed to enhance the air-water gas exchange. The series of experiments that have shown this have all, generally speaking, been completed on a still water surface. So there was a large series of experiments on fresh water, a couple of tests, but a couple of tests on salt water, but they've all been done on a flat water surface. The global gas exchange parameterizations all assume wind speed is the controlling parameterization. But what happens at low wind speeds? You have really low gas exchange rates. If rain is enhancing gas exchange rates, what is the comparison? So, is rain important there? Rain has also been observed to damp surface gravity waves. This has been known by people who've gone to sea for hundreds of years. And this is a significant impact on the microwave radar backscatter community. They use sea surface roughness to infer all sorts of parameters, including open ocean wind speed. If rain changes the sea surface roughness, their inferred values are actually wrong. Rain-generated turbulence was proposed 25 years ago as the mechanism for this damping. However, this has still remained unproven. Despite this, simple calculations can show that at low wind speeds and high rain rates, rain may be as important as wind in the mixing of and momentum transfers to the surface wave zone. But you're going, okay, low wind speeds, high rain rates. What does that mean quantitatively, and where does it matter? Shown here are satellite products, monthly average precipitation rates at the top, and monthly average wind speeds on the bottom for February 2012. And what you see in the monthly average precipitation rates is that in the equatorial regions, you have a higher precipitation rate, in this case, about 1 millimeter per hour. We're talking monthly averages in February. But what is important is that those same regions in the lower plot correlate to wind speeds of about 4 meters per second. So when I say low wind speeds, I'm talking about the order of about 4 meters per second. And these correspond to the highest rain rates we see in that same time period. So in the equatorial regions, we have areas of low wind speed and the highest rain rates. And so we have areas where rain may actually matter. So to start with, I'm going to present the results of a rain and wind-induced gas exchange study. And these experiments were completed in collaboration with Fabrice Barone, David Ho, Matthew Reed, Phil Gordon, and Wade McGillis, and were recently published in JGR. So in order to measure this, we completed a series of laboratory experiments. Measuring rain-induced gas exchange in the field is not quite possible at this point. The laboratory facility is a wind wave channel that is 37 meters long, 1.25 meters tall, and 1 meter wide. This facility has a recirculating pump that allows for current, that allows the gases in the water to be continuously mixed and allows for nice gas exchange measurements. The gas exchange technique we used during this was the SS6 evasion technique, and we had 2 sampling stations to ensure that our measurements were well mixed and that we had clean measurements. To simulate rain, we had 8 different rain simulators covering this flow. Within these 8 rain simulators, we had 20,000 hypodermic needles distributed randomly between them. And yes, they do come individually packaged. And yes, as a grad student, that was my job. So those 8 rain simulators covered 50% of the surface area of that 37 meters. Previous experiments had shown that it may not be physically realistic to just rain locally for a gas exchange measurement. So we covered 50% of the flow. What that actually looked like was each rain module was one of these metal trays, and as you can see, there's a lot of hosing involved, a lot of reservoirs just holding rainwater, and just a lot of plumbing.
Question?
Yep.
Was the height of your water injection great enough for the droplets to reach terminal velocity?
Not in this case. Here, we had about 40% terminal velocity. But if you did a Fruit or Weber number scaling, we did reach a sufficient value that the physics were the same as with terminal velocity, so we don't expect the secondary droplets or any of that phenomena to change, and believe that the values would scale as if they were at terminal velocity.
And do you have control over the drop size?
We do. By using the same size needle, you get a relatively narrow banded drop size, and we did measure that. Right here, there's a rain imaging station, so using a high-speed camera, we were able to image the droplets right before they impacted, and with that we got impact velocity in the horizontal and vertical direction and drop size values.
Why you didn't just use shower heads?
The issue with that is you have a less control over your drop size. You get a larger range of drops. Our drop size in this case was 2.6 millimeters in diameter, and that was near the peak of the natural drop size distribution and the volume drop distribution, so what you find in the field. A drop shower head will give you a unrealistic drop size distribution. It will give you a bias towards large droplets that aren't found in nature.
But we just hang it like we're really high, that's all.
But if you hang it really high, you lose the wind field. We place the rain modules here on top of the flume to preserve the wind field. We had a balance.
So you're trying to simulate the wind speed in the induced turbulent mixing as well
Right.
as in
Here,
addition to
right.
the rainfall.
Right. For this case, we had both rain and wind conditions, which was key. This experiment was to go, we know rain induces gas exchange. We want to know what happens when you combine rain and wind to affect the gas exchange. So our instrumentation for this, we had the two SF6 stations. We had a profiler which gave us wind speed, a profile measurement of wind speed with a sonic anemometer. And then on the water side of that profiler, we had a Vectrino ADV, which is a small scale ADV, to get profiled measurements of velocity and turbulence within the water column. We also had a wave gauge within upwind of that to get wave measurements simultaneously. And this is a picture of the sonic anemometer, which also gives you a nice view of the roof of the flume, which is now covered in needles. So with this setup, we had 3 rain rates, 8 wind speeds, for a total of 24 experimental conditions to cover a full range to get a really good idea of what the rain-wind interaction combination is.
One more question. You're using sulfur hexafluoride, which is quite a heavy molecule.
Yes.
Is the physics basically the same for lighter gases?
Yes. Although it's not shown here, we actually had carbon dioxide in the water too. We super spiked the tank with that as well, and we had the same results. So shown here is the gas transfer velocity from the SF6 measurements, normalized to a Schmidt number of 600 on the y-axis as a function of the 10-meter wind speed. So the tank measure wind speeds were scaled to a height of 10 meters using the law of the wall. And the symbol scheme here is no rain. Experiments are shown in black. A 30 millimeter per hour tank average rain rate is shown in blue, and a 60 millimeter per hour rain rate is shown in red. The symbol size here reflects the variation in rain rate. So a little symbol here shows that this rain rate was less than 30 millimeters per hour, and a larger symbol shown here in red here indicates that rain rate was above 60 millimeters per hour. Those large rain modules, controlling the rain rate in them was slightly difficult. So to indicate where the variation was, the symbol size does that for us. And what we found is that at low wind speeds, the gas exchange rate is significantly enhanced by rain. So with no rain, you have gas exchange rates of 10 or 15 centimeters per hour. With rain, but at higher wind speeds, the change with rain rate decreases, and that at the highest wind speeds, there's no significant change with rain. So
So
above,
are you getting breaking waves in these tanks?
at the highest wind speeds, yes, there's breaking waves.
Onset speed of,
I'd say around the 15 meters per second, there starts to be some breaking.
okay, so that's a lot higher wind speed than where the onset would be in nature.
Correct. Well, the breaking, when I say breaking, it's also at the end of the flume, not at the beginning. It's effective-ended breaking.
Because wave breaking really enhances your gas exchange.
Yes. So the limit for rain effects seems to occur at a wind speed of about 11 meters per second. So at low wind speeds, we see gas exchange affected by rain. At high wind speeds, there is no effect by rain. And as I said, we measured several dynamic parameters, but for the sake of time, I'm only going to show the wave height variance effect, where wave height variance is the integrated wave height frequency spectrum over a given range. Shown here is the 1 to 20 hertz range. And same symbol color as before. And what you see is that at 0 and 4 meters per second, the wave height variance increases with rain rate, as you'd expect. Well, as you'd expect at 0 at no wind, you're generating waves with the presence of rain. At 4 meters per second, you see the same thing, indicating that the ring waves generated by rain are actually bigger than the wind generated waves. So you have really tiny waves at the 4 meters per second wind. At 5 and 10 meters per second wind speeds, however, you see a significant decrease in the wave height variance. And this corresponds to the rain-induced wave damping phenomenon. However, at higher wind speeds, there's no change in the wave height variance. And what we see from this is that once again, there's 11 meters per second cutoff for rain effects. There's no change observed at higher wind speeds.
So the wave height is kind of tiny, right? Even at high wind speed, in this case 10 minus 4, so it's give you 10 minus like 7 meters.
That's meter square. Yeah.
Yeah, like you take a square root.
Yeah.
So the wave reaction is very, very small. Just curious because it looks awfully small. Because in the lab, I guess you have your wave tank is like how big? The number is read there is 10 minus 4 if I read. So they give you 10 minus 2.
That goes up to, above that, but yeah.
That's okay. Just
Yeah.
curious.
It's variance, so you
It's-
gotta take
it's
a
the
square root
variance.
of that.
Yeah.
To get a
Square
standard
root is 10 minus 2,
deviation,
that's
yeah.
1 centimeter.
And so, and then the currents and turbulence data exhibit the same cutoffs. So the conclusion is that we're seeing an 11 meters per second wind speed cutoff in all of our data, and we want to know why. So to investigate this, we looked at the kinetic energy flux. And previous experience had shown that the gas exchange rate scaled with the kinetic energy flux of rain. And using that previous data and adding our two no wind speed points shown here in the solid black, we fit the data with a power scaling law to develop gas exchange rate dependent on rate only. And then computed the ratio of the gas exchange rate from rain to the kinetic energy flux from rain to the kinetic energy flux from wind, which is well known, and call that parameter beta. And when you plot beta as a function of wind speed for the data, where our data from this experiment is shown in blue triangles and red squares, and a previous set of experiments is shown in the gray stars and blue crosses, you find that at low wind speeds, beta is greater than 1, and that at high wind speeds, beta is less than 1. So, and that cutoff where beta crosses 1 happens to be at our 11 meters per second wind. So our kinetic energy flux ratio seems to be a good indicator of where our rain effects are. And using that ratio, we developed a nonlinear model for the gas exchange rate, where the nonlinear model is a function of the gas exchange rate of wind using a quadratic parameterization, which is what you typically use for the wind parameterizations based on field data, and our rain gas exchange parameterization based on the wind, the no wind data, multiplied by an exponential damping function. And we found that the nonlinear model and the data agree relatively well with the R squared of 0.97. So using this, you go, okay, we have lab data, but lab data, what does that mean in the real world? So in the field. So to extrapolate to the field, we calculated the ratio of the rain component of the nonlinear model to the total gas exchange rate using the kinetic energy flux rate based on the loss partious drop size distribution, which is a field drop size distribution, as opposed to our lab one, which is pretty much a monodisperse. We, for the most part, had a single drop size and a gas exchange parameterization for wind for the field, in this case, Hoedal 2006. And using that, we were able to compile a phase diagram based on rain rate and wind speed to say when rain will matter for the gas exchange rate and when it won't. And so we find that at low wind speeds and high rain rates, we can say, okay, rain should be taken into account when computing the gas exchange rate. So at a wind speed of 5 meters per second and a rain rate of 40 millimeters per hour, rain will matter. Rain will be significantly influencing the gas exchange rate. However, if you increase that to a wind speed of about 15 meters per second, the rain is no longer going to matter. Wind is going to clearly dominate the gas exchange process.
And am I reading that correctly, that a delta of 0.9 means you're almost doubling the exchange rate?
That means a delta of 0.9 means 90% of the gas exchange rate is based on rain.
So the total is 1.9 times what you would have with the gas only.
Right. So where does this mean in the big picture? So here on the, going back to the satellite data products, this time for 2009, here blue indicates a delta of 0, red equals a delta of 0.25, so rain is contributing 25% of the gas exchange. And we find is that in the equatorial regions, especially in the summer months of June, July, and August, you see that rain can significantly enhance the gas, can be significantly enhancing the gas exchange rate. So in the equatorial regions, rain probably shouldn't be neglected when computing the local gas exchange rates.
But the area fraction of deep convection in tropics is about 3%. So that's about area fraction of rain even smaller than that. So we'll take that into account.
But that's
Only 1%
Right.
of the area.
Yes.
And you can
But this is also the region where there are large CO2 fluxes.
Right. But there's large CO2 fluxes, and a previous paper had shown that on a case study in the Western Pacific, that including rain actually switched the sign from a source to a sink in a certain area. So it can be important in terms of local fluxes.
Well, the sign is governed by the partial pressure difference.
Yes.
So I don't see, how's rain going to change the sign?
So it's not, it depends upon where the sources are, right? And so these areas in the tropics have large sources of CO2, there's a lot of biomass there.
I believe all that, but if the thermodynamics is driving the direction of the exchange.
Yeah, so the
and she's-
partial pressure is.
Because of the biology in the area,
Yeah.
because because the wind did not produce enough, the presence of rain induced overcame the biology in that area.
But that's similar. If it's only 1%, it means that rain should be at least 100 times more efficient.
Yes, so
To
rain
have
is more
the-
efficient
100 times?
in that area at the time.
100 times. Than without rain.
Yeah.
Locally instantaneous.
Yeah,
Yeah.
100 times. I didn't see it here.
Actually,
If it's 1% of area,
Yes.
then to make a difference, it should be
When
at
it-
least 100 times stronger.
It's her seminar, but
Right.
I do, I switch in the end.
Well, maybe a follow-up question. On your, way near the beginning, you had comparison plots of wind speed and rainfall. How were the wind speeds derived? Hopefully not by sea surface roughness.
Well, in that case, actually, in fact, wind speed would be overestimated, the wind speed would actually be lower. So,
Yeah, okay. We went.
That's standard technique actually. It's standard technique, it's actually.
all right. So switching gears a bit to the rain wave interactions. For these experiments, we actually built a smaller tank in my time in grad school. And this tank is 7.3 meters long, 60 centimeters tall, and 48 centimeters wide. And while this tank is much smaller and will produce shorter fetch limited waves, the advantage of this tank is that it provided a nearly 5-meter fall height for the rain, allowed us to get to 90% terminal velocity, and was completely composed of plexiglass. The main facility had a steel bottom and would not allow for the use of salt water. The plexiglass tank allowed for the use of salt water. So the rain simulator for this facility was placed as close to the ceiling as possible, which allowed for that large fall height. And for this experiment I'll be discussing here, it had a 1.3 millimeter drop radius, although we were able to switch out drop sizes much more easily and did later, and the 90% terminal velocity impact. And so for the rain wave experiments, previous rain-induced wave damping experiments, when they measure rain-induced wave damping, they made their measurements downwind of the rain area. And the reason for this is the instrumentation itself really didn't like to get rained on. A lot of things don't really like to get rained on. And this is a limiting factor in the sense when you go to compare results, sometimes the measurements are 5 centimeters downwind of the rain area, sometimes they're 10 centimeters. Some people like to measure 10 meters downwind of the rain area and call them results. So it makes comparing results very difficult. So in order to get around this, we used an optical imaging technique where we used fluorescent dye in the water and a single point laser and a camera system where the camera with a bandpass filter on it only saw the laser in the water, not above, and you've got a clean image of the oscillating water surface. But in order to compare our results to the historical data sets, we made measurements both beneath the rain and downwind of the rain. Downwind of the rain, we also used another traditional technique and made slope gauge measurements as well. Beneath the rain, we once again used a rain imaging camera to measure drop size and impact velocity. And upwind of the rain, we made wind speed measurements using a pitot tube in this case. A pitot tube is another instrument that really does not like to get wet. With this setup, we made measurements in both fresh and salt water using 4 rain rates and 5 wind speeds for a total of 38 experimental conditions, since we did not make measurements of flat water. So to start, we're going to look at the rain-only wave spectra, or the waves when you typically think of when a single droplet of water hits a water surface and generates those nice spring waves. So these spectra are for freshwater impacts and no wind. On the left are those generated beneath the rain, and those measured directly downwind of the rain. And what you find is that the peak in the wave spectrum waves are between 3 to 6 hertz, and that at rain rates of 50, 110, and 200 millimeters per hour, you see an increase in high frequency wave energy, although there is not really a significant increase between 110 and 200 millimeters per hour. You'll notice the rain rates are higher here, where we have 50, 200 millimeters per hour. That is the case because these are local rain rates, so these are the rain rates impacting that area. This rain module is smaller, it's raining over a certain area. But the measurements in this case are directly reflecting that rain rate over that area. So what is important in this case is the local rain rate, not the rain rate averaged over the entire zone, as in the previous gas exchange measurements. When you compare these results to downwind measurements, what you find is that the peak in the wave height spectrum is over the same frequency, 3 to 6 hertz, but the intensity of that peak is less, as you'd expect, as the waves have time to damp as they travel downwind. But the behavior at high frequencies is a bit different in the sense that all 3 of the rain rates are spread out. So there's a change in the behavior of the high frequency. So where you measure matters. For now to the good stuff, the rain and wind wave interactions. We're going to start with the measurements made beneath the rain. These are fresh water. And to explain the color scale here, the black spectrum is the wind-only spectrum. The purple spectrum is the rain-only spectrum, so what was shown previously. And the red is the measurement made when rain and wind are interacting. And what we find at the lowest wind speed used of about 6 meters per second is that the wind-generated waves actually occur at about 8 hertz, or have a peak at about 8 hertz. So they're actually much shorter than the rain-generated waves. And so the wind and rain interaction spectrum is nearly identical. This is essentially identical to the rain only. So this is a fetch-dependent phenomenon. At a higher wind speed of 9.5 meters per second, the rain-generated waves are being injected at the same frequency as the wind-generated waves. And so we see a slight decrease in the peak frequency compared to the wind-only spectrum, but otherwise this most significant feature is that there is a significant increase in high-frequency energy being observed. At higher wind speeds, there is a small change in low-frequency energy. There's a small decrease in low-frequency energy observed, but once again, there's a high-frequency energy being injected by the presence of rain. And the same is true at the higher wind speeds. So in order to examine all conditions for both fresh and salt water, once again, we calculated the wave height variance. But this time, because the largest signal we were seeing was in the high frequency range, we focused on that and calculated the wave height variance for 8 to 20 hertz. And what we find is that the wave height variance increases with rain rate over all wind speeds in both fresh water and salt water. Now, if we do the same examination, but this time downwind of the rain, we do see something different. And at the lowest wind speed of about 6 meters per second, we see damping at high frequencies with the presence of rain. And then there's only a small increase in low frequency energy, but over a very narrow band. And this is a side effect of the fetch dependence once again. At all other wind speeds, we see the more traditional observed recorded behavior. So at low frequencies, we see a decrease in the peak wind wave spectrum with the presence of rain. And that decrease in energy is observed at higher frequencies as well. At higher wind speeds of 13 meters per second and 16 meters per second, there's only a decrease in high frequency wave energy observed. So when we went to calculate the wave height variance for the measurements made downwind of the rain, we investigated the low frequencies only, in this case, 1 to 8 hertz. And what we find is that at low wind speeds, we see a decrease in the low frequency wave height variance at 5 and 10 meters per second wind speeds, and no significant change at higher wind speeds. And in the case of salt water, we see the same. But what is interesting to note is that if you look closely at the 10 meters per second case for fresh and salt water, there's an increase in damping observed in the saltwater case compared to the fresh. So to summarize that, the experimental setup, or short fetch, did limit the measurements of wave damping beneath the rain at the low wind speeds. However, so that's shown here, beneath the rain at high frequency waves, there was wave generation measured at all wind speeds, which had previously been not measured. You didn't measure the high frequency wave generation or the ring waves downwind because the high frequency waves damp out if you're measuring downwind. but the ring waves are generated. Downwind of the rain, you measure wave damping at low wind speeds and low frequencies. And at high frequencies, you measure wave damping as well. So you don't measure the ring waves. So there is significant variability observed between the two measurement locations. And this is compounded when you consider salt water. So although it was difficult to see, for salt water, there is a decrease in the amount of wave generation observed beneath the rain for the case of salt water. And there is an increase in the amount of wave damping observed downwind of the rain. So they're countering effects for the case of salt water. So where you measure becomes even more important when you're trying to compare literature. So going forward, to be consistent and try to compare results, ideally you should measure beneath the rain, even though in our case we had fetch limited measurements. Which brings us back to rain-generated turbulence and this video. So rain-induced gas exchange. Gas exchange primary controlling mechanism is near surface turbulence. Rain-induced wave damping. Several years ago, Simplest had proposed that rain-induced turbulence was the source of the rain-induced wave damping. But that has remained unproven because making rain-generated turbulence measurements have proven difficult. They've proven difficult because as you watch this video, you see that near the surface you have multi-phase flow, you have these bubbles. ADVs don't really like bubbles. And you have this turbulence layer being generated really near the surface, and a lot of techniques have difficulties making measurements near the surface. In addition, you have these large craters, and lasers and spherical craters combine to reflect laser light straight on into your camera. And your visor, once you do that, really doesn't like it. But that can be overcome after a few years. And what you find to do that, for this set of experiments, we use an optical wave gauge described previously. And to make the turbulence measurements, we used a modified version of particle image velocimetry, which I will get into greater detail. But for particle image velocimetry in LIF, we had 3 overlapping fields of view directly beneath the rain, marked 1, 2, and 3 right here. Our rain imaging camera, and then downwind of that area, we had a temperature conductivity probe that was profiled once every 5 seconds to get 100 continuous profiles of density through a 10-minute experiment. And a pitot cube. Each one of these experiments lasted 10 minutes. So we'd start our data acquisition, then we'd start the rain. So we'd capture the transition from no rain to rain, and then we'd let each rain experiment transition from no rain to a steady state rain. So you'd get the nice smooth transition as the rain rate increased, and then we'd have an instrument to mark when the rain rate hit steady state, and then we'd have at least 5 minutes of steady state rain data recorded. So we'd have a nice time series of rain data for 10 minutes of data acquisition. Each one of these, for all these instruments, we had completed 70 different experimental conditions, including fresh and salt water, 7 rain rates with 2 drop sizes between them, and 5 wind speeds. I will not be discussing all of that today. I will be discussing 3 of those. And that would be 3 rain rates and no wind on salt water. So, to give you a brief overview of the experimental techniques, for those aren't familiar, particle image velocimetry and laser-induced fluorescence are 2 imaging techniques used to derive velocity and turbulence fields for PIV, and laser-induced fluorescence was used to derive the changing density fields. PIV uses lasers and particles to get 2 images separated with particles as the particles follow the flow field. So you have 2 images, you know these particles are, if they're following the flow field and they know the time between, you can calculate how far the particles displaced between them to get the velocities.
So you somehow, you don't do this by hand, they've got some machine that you train to recognize that this is particle alpha and this is beta and this is
Right,
gamma.
you can, I wrote the MATLAB code to do it. But, and the laser-induced fluorescence uses the intensity of the image background to infer the density where we're raining dyed water on less dyed water, where we know the salinity of each original dyed intensity. And we're doing that simultaneously. But as you can see, trying to identify the particle displacement in those top images is a mess, where trying to identify particle displacement in those bottom images is nicer. So what you do is you remove that dyed background from those top two to get the cleaner images to run the correlation analysis on the particles. But part of the issue is with the PIV is you want to know where that exact surface is. And for most PIV experiments, you use a separation time between you take those two images so that your surface doesn't move significantly. With the rain problem, you have two velocity scales. Your turbulence velocity and your surface velocity, because of that crater generation, are about 2 order magnitudes apart. So here we had to make the assumption, we had to choose, and we wanted the turbulence velocities to be high resolution. So we let the surface move, determined where the surface was in both images, calculated a minimum surface, and used that, called that our surface. We had to pick the lesser of two evils, and we went for the higher velocity measurements. But what that actually looks like is that when you do that, combining field of views 1 and 2, we could assemble a velocity field shown here on the left, and show about 1/64, I think, of the velocity measurements are actually shown on that plot. Because I think I'm showing one of every 8 in each direction. To assemble a velocity field from the PIV values, and its corresponding vorticity measurement is shown on the right here for the PIV measurements. And then for LIF, you can use the background of that image to derive how the density field is fluctuating. So as these are 3 snapshots in a 10-minute experiment, and as it continues to rain on a flat surface, you can see the density change, and you can see a freshwater lens forming. So that's where those 2 raw images that look like scattered dust convert to velocity fields and to density fields. So for the data, as I said, we also had that profiling temperature conductivity profiler, and that data is shown here. And the units, the z-axis shown here is z eta, so this is the z reference to the instantaneous surface. And the time axis is time after rain, where the solid bar indicates the time rain starts, and the dashed line indicates the time rain has reached a steady state. And as you notice, those change with rain rate because it's easier to reach a lower rain rate. It takes less time to reach the lower rain rate than it does to reach a high rain rate. So for these experiments, we had rain rates of 40, 90, and 180 millimeters per hour. And here density has been normalized by the bulk density. And what we find is that for a rain rate of 40 millimeters per hour, we see that a freshwater lens of about 5 centimeters deep develops over time, and it seems to remain relatively stable, although it does increase in freshness towards the end. About at 90 millimeters per hour rain rate, the scales do fluctuate. This is 0.8 scale, 1.5 and 2. The 90 millimeters per hour, the density changes are stronger, still about 5 centimeters in depth, and increase significantly over time. Something is significantly different at 180 millimeters per hour. As you notice, the freshwater lens is shallower. It's about 3 centimeters deep instead. It doesn't really deepen. It gets significantly fresher sooner than the other 2 rain rates, but it never actually deepens. For now we have the turbulent kinetic energy results for the same 40, 90, and 180 millimeters per hour. The z-axis, instead of being referenced to the instantaneous surface here, is referenced to the still water surface instead. But the same time scale is applied. And what we find for the turbulent kinetic energy is that we can see a high intensity turbulent kinetic energy layer that's about 2 centimeters deep just below the surface, which does indicate why people have had so much difficulty trying to measure it. If you try to measure a 2 centimeter layer just below the surface with an ADV that's multi-phase, can be multi-phase flow, you're trying to measure nothing with an ADV. And what you find is that periodically throughout this flow, you have bursts of energy going down through the depth corresponding to single rain droplets penetrating past the stratified layer, that freshwater lens that develops, and you get these little raindrops that make it past that layer and penetrate down to depth. And they happen intermittently throughout the flow. And they're making, generally speaking, on average, about 10 centimeters, occasionally a little bit later. At 90 millimeters per hour, that high intensity turbulence region, a little deeper, that secondary layer is further deeper, and the intermittent raindrops that penetrate past it are more frequent and make it to a deeper depth of about 15, 16 centimeters. The behavior at 180 millimeters per hour is markedly different. The turbulence layer near the surface is not nearly as high, comparatively, because they're all on the same scale in this case, compared to 90 or 40 millimeters per hour. And there's a drastic difference when it comes to that intermittent behavior. There isn't any. Nothing is making it past that freshwater lens that develops. So there is no deep turbulence mixing in the case of 180 millimeter rain rate. Now,
just past 100, is that one instance of something penetrating?
yeah, there's one, maybe two occasions compared to the repetitive behavior at the lower rain rates. Now, if you take this time series of turbulent kinetic energy profiles and average them in time from 150 to 300 seconds, and average them in depth from 0 to 15 centimeters, you can calculate the average turbulent kinetic energy. And what we find is that the average turbulent kinetic energy increases from 40 to 90 millimeters per hour, and then rapidly decreases at 180 millimeters per hour.
Is it because you create a lot of bubbles? I mean, air bubbles?
Nope. If you compute the same thing, but this time if you calculate the turbulent kinetic energy dissipation rate, you see the same thing where turbulent kinetic energy dissipation is negative, so it decreases from 40 to 90 and increases from 90 to 180. And the reason for this, or at least the reason I believe, is that both the turbulent kinetic energy and the dissipation rate decrease significantly at the highest rain rate because of buoyancy effects. So when you start raining, as expect, you start mixing things up. You rain enough and you rain hard enough initially, you start raining, you develop a freshwater lens. You develop that freshwater lens too fast, that rain is not going anywhere. Keep raining, keep developing that freshwater lens, it's not making it past it, so the fresher it gets, the less likely it's going to continue to mix.
Could you go back a couple of slides, because around 300 seconds it looks like the depth of penetration does increase on the bottom.
On this one?
Sure. Yeah.
All right. That is actually an artifact of the mean flow, and there shouldn't be a mean flow because this is a no-win case. And the issue with that is that, although you can't see it, is that because this is a no-win case, that freshwater lens actually went out, bounced off the side of the tank, came back. So there is a mean flow associated with this, and it's a mean U, and it's a gravity current, although I'm not showing it. And so this is an artifact of removing the mean. to calculate the turbulent quantities here, because it's unsteady flow, I average spatially among my images, because those velocities I showed, I had about 300 measurements horizontally and 500 vertically. And because it's unsteady, I average spatially to calculate vertical profiles of turbulence. Most cases for PID, you average in time, remove the time average mean, and you get better convergence, you have more data. That is an artifact of the mean flow, and because it doesn't completely remove with my averaging over 300. But the largest assumption with turbulence statistics is that it's steady. And this problem clearly is not steady. And that was one of my advisor, we planned these experiments, and it was one of those, we hadn't really thought about the fact that we weren't going to be able to use traditional turbulence analysis with our data. And then I looked at this and went, okay, we're not treating this as steady, try again. But that is because we actually generated a gravity current.
But did you do control experiment when you have all fresh water and you still should have monotonic behavior, right?
Right.
Did you do that?
Yeah, that is a gravity current, and when you make estimates of that, that is the remainder of the gravity current.
No, I mean, if it's not salt water, it's fresh water, and so you don't have this effect at the
Right.
slide.
You
Then you have monotonic increase of kinetic energy with rain rate?
Right, you see the increase with, yes.
Then
We have a full set with fresh water, and I'm certain this trend is not, I'm certain this is a saltwater trend, it's not something else.
This lens that you're showing us is not pure fresh water. It's diluted.
It's not pure fresh water. It's
largely
reduced,
salt and
right.
a little bit of fresh.
It's, instead of being 37, we were rating on 37, we were rating on a density of 37, it's basically 35.
Okay, that
Something.
was throwing me. All right, thank you. Yeah.
And
But you
when I say freshwater lens, I mean reduced density.
But you still have a buoyancy effect even between 37 and 35.
Correct.
Okay.
And I'm going to show you that it is buoyancy. But how can I prove it's buoyancy? We measured the fluctuating density with the LIF. So, with the buoyancy flux, when it's positive, you have buoyancy production of kinetic energy, turbulent kinetic energy. When it's negative, you have buoyancy destruction. So if you look at this, at the lower rain rates of 40 and 90, the buoyancy flux in that mixed layer of about 6 centimeters, positive. At the 180 millimeter per hour, it's negative, indicating there's buoyant destruction of turbulent kinetic energy at that rain rate. And if you average them over depth, you in fact see that there is a trend, negative trend in the buoyancy flux. So that even though it is still positive at 90, the buoyancy flux is decreasing at 90, indicating that buoyancy is starting to overcome the turbulent generation. So in terms of a scaling parameter, how do we actually understand this? So the small scale Froude number is a ratio of the inertial forces to the buoyancy forces. And if you examine the small scale, and it's large when inertial forces are winning, and small when the buoyancy forces are kicking the inertial forces away. And what we find for the high rain rate case is that the small scale Froude number starts out near the surface when mixing is just started. It's large, it's about the order of 1,000, and that over time, even within 100 seconds after the start of rain, small scale Froude numbers drop by an order of magnitude, and that by the end of the experiment, near the surface, the small scale Froude number is dropped by 2 orders of magnitude. So it's a very time dependent process, and that as you continue to freshen the system, buoyancy forces start getting larger and overcome the turbulent mixing process that rain would be generating and slow the mixing process down. At 90 millimeters per hour, you see the initial small scale Froude number of 1,000 once again, but it takes 500 seconds this time for the initial first order of 1 order of magnitude decrease. At 40 millimeters per hour, 500 seconds isn't enough to significantly drop the small scale Froude number to the surface by an order of magnitude. But I propose that if you let that low rain rate continue over time, you would see an order of magnitude drop, given enough time, enough rain on the system. If you calculate the average small scale Froude number for the 3 rain rates, you see that the average Froude number decreases with increasing rain rate, as expected. But if you compare that to the turbulent Reynolds number, which is a ratio of the inertial forces, this time to the viscous forces, you see the turbulence Reynolds number increases from 40 to 90, and then significantly decreases from 90 to 180. So what this indicates is that although buoyancy forces increase from 40 to 90, the turbulent mixing increases enough that is still increasing enough that it does not overcome viscous forces at 90 millimeters per hour. At 180 millimeters per hour, the buoyancy forces get strong enough that the viscous forces can overcome the inertial forces and result in the damping of the turbulent energy, and the mixing by rain becomes less efficient and gets damped out. So to summarize, rain significantly influences the gas flux, especially at low wind speeds. The first measurements of rain-wave interactions have been completed here directly beneath rain, with wave damping observed at low frequencies and wave generation at high frequencies. And the measurement location for these is very critical. And that turbulence measurements beneath rain falling on a still surface show that initially turbulence levels will increase with rain rate, but then turbulence levels decrease when buoyancy forces take over at the higher rain rates. And then to really summarize, to wrap this up, we had this phase diagram at the end of the gas flux. So what the turbulence, the saltwater turbulence results indicate that this picture does change a bit. So at low wind speeds and high rain rates, rain-generated turbulence enhances gas exchange and damps surface gravity waves, despite buoyancy. But at a certain rain rate, rain effects are going to be limited by buoyancy, whether that is where you initially rain too much, or you start at a lower rain rate, and over time, buoyancy effects actually take over. So you either start by raining way too much, or you start at a lower rain rate, and over time, buoyancy effects will start limiting. And that's what I have.
Thank you so much. So, anybody else comment?
Yeah, back to the rain-wave interaction. Your waves, as Company had pointed out, what you're producing about a centimeter high. You didn't quite say how long they are. I assume this would be short scale, almost on the drag scale, right?
Mm-hmm.
And so could the interaction which you imply, this could be at the high frequency range. This could be because you can't distinguish what the rain is producing and the ambient wave which is there. If they were bigger wave, your waves were say bigger, let's say 20 centimeters, would it be the same?
When the rain is at a lower frequency than the waves, it's indistinguishable. When the rain is clearly being injected at a higher frequency than the waves, the effects are going to translate.
But I probably elaborate, because basically, because in your lab it's fresh limit.
Right.
So your wind does not really generate what we call real waves because they're so short. So let me finish. So you actually have another axis if you think of real world, because in the real world there are the real waves there.
Yes.
And the wind, even at low speed, will interact with that waves.
Yes.
So in that sense, that's actually, out of these two axes, there's another axis where describe the ambient wave conditions. It doesn't have to be big wave, big swell.
No.
And that affects really not being static. You know, I assume you can actually generate waves and let wind blow. You see what I'm trying to say?
Yes, and there have been studies on mechanical waves as well,
Yeah.
and you can dampen mechanical waves as well.
Then you can try to do the same stuff. Because it's really another axis when you try to apply to real world. Because the real world, given the wind speed, that's actually waves there. You know, that the picture you show on the global scales. The wave is not, wave is actually there. Waves are everywhere.
Yes, and there have been studies with mechanical waves that show damping at all those frequencies. In the smaller tank, there were, for my dissertation work, there were two main, we switched to the smaller tank because it gave us the impact velocity in the salt water. We could not get all three. We could not get the bigger waves, salt water, and the impact velocity. And let's be honest, a member of my committees wanted the salt water and the impact velocity, they won, as they were controlling my degree. But for the turbulence, for the cases where we could not measure rain-induced wave damping directly beneath the rain because the waves weren't there, at those wind speeds, there's a very large shear current. We do see interaction between the rain and the shear current. That shear current decreases, so there is a turbulence interaction there. So although we don't see it in wave height, we see it in the turbulence results and the velocity results that I did not show here. I didn't show them there because the turbulence wave coupling is a slightly convoluted problem in the sense that when you go to, I'm measuring rain-generated turbulence that affects that wave damping problem, you're actually measuring a decrease because it's a coupling. So it's a slightly more convoluted problem. But, so while we don't measure the height issue, we do measure the turbulence signature of it. So I'm less concerned about the fact that we didn't measure the height. And yes, there are waves there, and you can measure it in the wave generator issue. So it's more about finding the best facility until we can scale it to the lab that actually we can put salt water in it. It's just more of, I had two facilities and neither one of them was perfect. And I went with the one that provided me 2 out of 3.
So how would you translate your picture now to explain to people running DCMs, because you've skipped one of the big components, the wind waves, so that what you drew here is in the absence of the wind waves, right? But in the real world, you do have. How do you modify this to give it to the people running DCM? Because if you're giving them that, this is almost, for the lack of a better word, almost misleading.
And what's misleading is that what this really needs is the time axis. What's missing from this is that it's not showing as the time axis. What's really missing is from this is that the time axis
You know,
is
like a
needed.
flash. But I think your
It's-
argument,
the flash is not-
you will say that the wind generated shear so strong that maybe they are bigger than the typical waves in
Right.
the first 10 centimeters.
Right.
Then this would be fine. So
Yes.
I follow your argument.
Yes, the wave height issue is an issue.
May not be
But
serious.
I think, although I didn't show it, the turbulence data, I think, does a better argument of supporting the wave height data.
So reduced to a skin roughness.
Right,
The scale may be different.
yeah.
Talking about global issues, so just a different type of question. So how these things affect SST, in terms of non-wave radiation? If you have a ring versus no ring, in terms that, because that got to be different. Right? It will affect the SST.
Yeah,
You see what I'm trying to say?
yeah, rain affects the skin temperature.
Yeah, you will have to, right? Because of all
Yes.
these turbulence. So anybody study that?
Well, Anderson and Weller did all that stuff on how the effects on the next layer.
Yes.
Yeah, but they are not that precise. That's kind of cheating.
No.
No, I'm talking about
And that,
that.
well,
I'm not talking about
any field work that's been done on rain, it hasn't, I mean, it's really, that type of work has really been, we've been out there and it rained to see what I can do. And that's part of why, I mean, all my work was done in the lab, because part of it is you can fund it, and you can try to convince someone to fund it, because they can send you out there for 2 weeks, and you can go out there and get nothing.
So anybody try to do in the lab, try to measure how the ST is affected by rain?
We didn't, because we didn't have the conditions to control the temperature that closely.
So it's hard.
So that is difficult. All of the density changes we had were completely salinity based. I mean, we measured the temperature, and the slight fluctuations in temperature were considered in the density, but they were not the controlling parameters of the density changes.
Again, your effect is only 1% of the area.
Because that's really much more important from the global warming perspective, because you are in a region where you get the biggest low
It's
aggregation.
1% of the area again, where it's raining.
Yeah.
1%.
How much?
1%.
1%?
It's a global
Based on
number?
your model, or?
It's deep convection that we're talking about. That's where significant rain is coming. It's about 1% of the area.
1%.
Even in ITCZ.
At a given time.
Right.
To that.
But that's
What's the
based-
chance of raining right now? 1%.
No, in the area. In ITCZ, where we believe that it's raining all the time, but it's only 1% of the area. So your effect
But
is
does it have to be
very
raining all
local,
the
very
time?
localized.
It's very localized.
And then it's mixing
So it doesn't rain all the time.
everywhere. It's not
Okay,
frontal.
probably, we should thank Emily Harrison for such a thought-provoking.
We don't trust modelers.
Oh.